Okay, well, it's 9:30, so I think we'll make a start. Good morning, everyone, and thanks for attending the latest in our series of webinars on fires. If you haven't been able to catch the others, then I encourage you to go and take a look. I understand they're available on our website. Go and have a look at them. There were some fascinating subjects. For me, I'm going to be taking you through lithium-ion batteries and fires. If you have any questions, then feel free to pop them into the chat, and a colleague will collate them and we'll do them at the end. So, why are lithium-ion batteries so popular? It's all about energy density. So these two charts are trying to say the same thing in slightly different ways. The great thing about lithium-ion batteries is they have a very high energy density. The chart on the left is showing the energy density in terms of volume on the vertical scale and weight on the horizontal scale. And just for reference, the conventional lead-acid battery that may have been in the car is still in many cars, is the yellow circle. It's quite heavy, it can contain a lot of energy, but it's quite big. Moving through the nickel cadmium and nickel metal hydride batteries that we're used to having, they're better, but not so good. And lithium-ion batteries run away with the story because you can pack so much energy into such a small space. And the diagram on the right is saying the same thing, in that early days, when we first started using lithium-ion batteries, they were limited to fairly small applications, such as communications devices. But as the technology in the batteries has developed and our own technology and demands have developed, the demands for energy density from the cells has increased through e-mobility, e-transport and power tools, up to large applications such as uninterruptible power supplies and obviously, of course, EVs. Now, just briefly, how about a lithium-ion cell operates? It's the same as any cell, really. You have a container. Inside that, you have two electrodes, an anode and a cathode, and some electrolyte between them. And during operation of the battery, ions flow from one electrode to the other, depending on whether you are charging or discharging the battery. And the thing with lithium-ion cells is the choice of materials used at the electrodes and in the electrolyte between them means that it's lithium ions that are doing the flowing backwards and forwards, hence the term lithium-ion battery. And one of the key things to note is from a fire point of view, the problem with lithium-ion batteries in the most current and most common form is that the electrolyte is actually an organic flammable substance. So they come in all sorts of shapes and sizes. You get rectangular prism cells, which are in a small sort of plastic package, rectangular pouch cells for integration into products, which are, as the name suggests, they're packaged in just a foil flexible pouch. And far more commonly, you have the cylindrical cells, which tend to get used in power tools, electric bikes, e-scooters, EVs. And you have a metal case. They run at about 3.7 volt terminal voltage. That just falls out of the chemistry when you're using a lithium-ion battery. And so in order to get more useful applications from them, you often connect them both in series and parallel to get a higher voltage out of a battery pack and get greater capacity. And it's connecting several cells together that gives you a battery, which is where the term comes from. And this is just to give an idea of just how much of an increase in density there is. So these are CT scans of a slice through conventional cells. On the left-hand side is a standard non-rechargeable alkaline cell with the electrodes and the electrolyte shown there. In the middle, you've got the older type of rechargeable batteries, the nickel metal hydride, which has a much larger electrode area because you create two large plates with the electrolyte between them, roll them together, stuff them in the can, gives you a large surface area, much more power can be stored. And the lithium-ion battery really extends that concept, but you can see just how much more densely packed it is. And with cells and lithium-ion batteries, it's all about the choice of chemistry. That will determine ultimately what performance you get from it. And the graph here is showing the energy density on the vertical axis, different types of cell chemistry on the horizontal axis with the lead acid lower right. And the light blue are all the various forms of lithium-ion battery chemistry. And you can see there, you can get quite a dramatic change in the energy density you can get from it. But the different chemistries also have different disadvantages and advantages. So the current common chemistry is the NMC, or nickel manganese cobalt. And compared to that, The lithium manganese oxide and lithium fluorophosphate cells offer better power, but also some better thermal stability. And by that, I mean they're less likely to go into thermal runaway. More about that later. Compared to those, the lithium titanium oxide has a lower capacity, but it does have a longer lifespan and is better in cold weather. So if you're trying to build EVs that you're going to be selling in countries that are very cold or have very cold parts of the year, that's something you need to think about. And some of those early chemistries were not as stable as the ones we are currently using. And in particular, the LFP batteries that are now replacing the nickel manganese cobalt are less prone to a flaming fire because the chemistry means they produce less oxygen if they do go into thermal runaway. But the downside is they produce hydrogen instead. So you skip the fire and have an explosion risk as an alternative. And a really important thing with lithium-ion batteries is operating them in the safe operating area. So this chart is really trying to show that there's a range of temperatures and a range of voltages that the cell is quite happy to operate at, and that is the green area in the middle of the chart. If you start to operate it at a voltage or a temperature outside those, either too high or too low, then the cell can be damaged in some way, which either means it goes into thermal runaway, or it might be damaged internally if it's over discharged and the voltage gets too low, and it might go into thermal runaway later on. And there's a similar concept for charging. This chart shows discharging. With charging, there's nothing on the left-hand side of the 0 degrees because you're not meant to charge them below 0. And again, for current versus temperature. So there's a range of parameters that you need to keep within a safe operating area in order to use your cells safely. And the way that's enabled in lithium-ion batteries and cells, the protection systems are built into sometimes the cell, the battery, the device that's using the battery, and also in the charger. And the protection systems monitor the temperature of the cell to prevent overtemperature. There are some that look at the pressure in the individual cell. So if the pressure starts to increase, if the battery begins to fail, there's an automatic venting process. Short circuit protection is monitored by battery management units also, in order to keep the charging process and the discharging process within those bounds of voltage, current, and temperature. And as well as that, where you have lots of individual cells connected together to form the battery, you monitor the charging process to ensure the cells remain balanced so that all the cells get an equal amount of charging. And if a cell starts to become weak and gets overcharged, that can be noticed and acted upon before anything goes wrong. So just an example here, the lithium-ion battery from a laptop back in the days when you had interchangeable batteries for your laptop. And inside you've got a number of cylindrical cells that have been connected together in series to get the voltage that the laptop needs. And you can just see the edge of a printed circuit board there, which is the battery management unit, and that's providing the electronic protection for the cell. And a larger example here, this was taken from a hoverboard. And what you have here, in order to get more power out of the battery pack, you have a number of groups of lithium-ion cells that have been connected together in parallel, and then the groups are connected in series to give you an increase in voltage. So you get both the higher voltage and the high capacity that's needed by the drive system for the hoverboard. And in this case, the large PCB in the back of the picture is providing the battery protection function. So why are lithium-ion batteries a problem? Well, it's all about energy density again. And I want to emphasize that lithium-ion batteries don't always go bang. A lot have non-energetic failures, and you may have experienced some of these yourself. And this is where the cell has a loss of capacity. The internal resistance of the battery increases. Sometimes you can get delamination of gassing, and that's what's shown in the picture here. We have a mobile phone that's popped open because the pouch cell, flexible cell, has expanded as the battery has failed. It's a process that occurs over time, and it's benign, so nothing more dramatic happens, although it's very inconvenient. But of course, there's also the more energetic failures of lithium-ion batteries, and this involves the process of thermal runaway. And this begins to happen if the heat generated inside the cell during discharge or during charging is larger than the amount of heat that can be safely dissipated. And so the internal temperature in the battery starts to increase. And the chart on the right is showing that there is the safe area for the cell, which is below about 80 to 100 degrees. And once the temperature goes above that, there are a number of different reactions and breakdown mechanisms that can occur within the cell. And these lead to parts of the cell and constituents that would normally be kept separate coming together. They can react with each other exothermically, and other reactions also produce heat. So you get this problem that once the cell reaches a certain internal temperature, you get a breakdown process that gradually continues to increase the temperature, and eventually the pressure and temperature in the cell increase to the level that the cell ruptures. And so typically what happens is the internal cell temperature increases, the pressure increases, and where cells have a pressure relief vent, which is very common in cylindrical cells, you then get venting from the cell. That's where you get the cloud of gas being ejected. Now that gas has flammable components in it. So if there is a nearby ignition source, or if sparks are emitted from the cell as it's failing, you then get ignition of the venting gas, which is what produces the flames that you've probably seen in numerous videos. And the cell contents themselves can sometimes be ejected. And the problem is if one cell goes into thermal runaway in a battery pack, the heating of that cell can then cause the adjacent cells to begin heating and send them into thermal runaway. So you get this propagation of the failure mode from one failing cell through the other healthy cells in a battery pack to get a much larger failure. And I've always thought that the smaller cells, the individual cylindrical cells, you can think of them as being a little bit like a firework when they fail. And they vent the gas and they produce flames. It's a bit like setting off a firework in a room. So you can get a much more well-established fire much more rapidly than with a more conventional accidental cause of fire, electrical fault in an appliance. And of course, with larger cells and batteries like those we're seeing in e-bikes and e-scooters, you get an even more volatile reaction. So when fire brigades are turning up to fire started by lithium-ion batteries, they're finding they're far more well-established already. And the thing with thermal runaway is it's an internal problem. So the protection systems are there to stop the cells and the battery from straying outside that safe operating area by controlling cell voltage and current to ensure the temperature remains safe. They're aiming to prevent thermal runaway. But once the thermal runaway begins, the external protection systems can't really do much to help. It's just a chemical reaction after that. So firefighting needs to deal with both the flaming fire from the venting gases, but it also needs to cool the cell to try and stop the thermal runaway process. And the problem can be that sometimes the lithium-ion battery packaging or the packaging of the product that it's in can limit the ability of the firefighting water to reach and cool those cells to stop the thermal runaway process. And the process through which the gases are produced during thermal runaway is still not really fully understood. Although what is known is it's quite a nasty mix of gases. You've got carbon monoxide, carbon dioxide, some hydrogen, various sulfurous oxides, oxygen, hydrogen fluoride, hydrogen cyanide, methane, ethane, amongst others. So when they fail, that cloud of white gas that comes out is quite nasty. And the actual composition you get seems to depend on the state of charge of the cell. And the failure behavior is not entirely consistent either. Generally speaking, cells that are at a higher state of charge are more likely to cause a fire, those above sort of 50% or more, but not always. And those in a lower state of charge generally just generate gas, but it's quite a lot of it. And the gas is also conductive. So this can lead to consequential electrical failures if you have a cell that fails inside a piece of operating equipment. Another emission that come from a lithium-ion battery or cell when it fails include traces of the plastics that were used to form the cell, as well as remains of electrolyte and nanoparticles from the cathode. So what are the causes of failure of lithium-ion cells? And there's a range really. Some of them are essentially defects in manufacturing. So either the electrochemistry of the battery of the cell has not been very well produced, or the way the cell has actually been manufactured and put together has a defect in it, which may lead to an internal short circuit developing later. So any contaminants introduced into the manufacturing process. There are some environmental aspects. So for example, if a lithium-ion battery is not designed carefully to stop water from an application where it's used outside, water can get into the cell, can cause corrosion and can cause a problem. But there's also a group of faults that are essentially down to defects in how they are being used. So these are mechanical abuse, dropping and causing damage to the battery pack, thermal abuse, not allowing it to cool when it's being used, electrical abuse, using the wrong sort of charging equipment. Something that's being seen a lot is DIY battery replacement and tampering. I'll touch more on that a little bit later. And environmental aspects again, and this time it's on the user trying to use the battery-powered device in an environment it's not been designed for. So perhaps something that's not meant to get wet, they're using it in a wet environment or allowing it to get wet. And more on the electrical abuse. So it's really a use problem, and it's becoming quite common. And the picture here is really trying to represent that many people have got a drawer like this, and I have at home, where you've got a collection of various chargers that you've gathered over time. And the problem is that it's not always clear which charger is to go with which product. And sometimes the connectors are compatible. And it's entirely possible to plug the wrong charger into the wrong product and end up with a mismatching pair. And that leads to problems in how it is being charged. Or you maybe end up using a power supply that isn't actually a charger and doesn't have any charge protection mechanisms in it. Users can sometimes over discharge the cells or charge them with too much current or current for too long. Cells left discharged can actually degrade internally in a way that develops into damage in the cell, and means there'll be a problem when the cell is recharged. And sometimes the battery management systems will shut down a battery that's been excessively discharged so that it can't be recharged. And what's also being seen is people tampering with the cells themselves to try and get more performance out of them. Or if a cell management unit has discharged, cell is discharged too much and the battery management unit has shut down the cell, people bypassing the battery management unit so they can start using the cell again. And there have been some cases of users of e-mobility, e-bikes, e-scooters, uprating the motors to try and get more performance from the vehicle. So this is just an example of what can happen. I'm sure you've all seen videos like this before. Here we've got a lithium-ion battery pack that's intended to be charged at about 8 volts, running at 12 volts, just down in the bottom of the screen. And that's a very typical reaction. It's charging for a short period of time, and depending on the state of charge it was in when you connected it to the charger, eventually the excessive voltage causes the battery to go into thermal runaway. You get venting of the gas and you get flames. But the cells are tested to some degree. So lithium-ion batteries and cells are classified as dangerous goods. So when it comes to shipping them around, they have to go through some form of testing to check that they will be safe when transported. And the table there just gives you an indication of the different types of tests that batteries and cells are meant to go through before they are transported, to ensure that if they run into the sort of problems that could happen during transportation, that they remain safe. So it's not like these things aren't tested at all. However, we are still seeing incidents. And the Office for Product Safety Standards recently produced a report last month particularly focused on research around problems being seen with personal light electric vehicles, or PLEVs. And some numbers from them and from London Fire Brigade. In 2017, there were 2 incidents involving personal light electric vehicles. By 2023, it jumped up to 178. So a very rapid increase in the number of problems being seen with fires associated with e-mobility products. And in terms of actions being taken since 2022, there have been 21 product recalls, 29 product safety reports, and 26 withdrawal notices to retailers who have been found to be selling e-bike batteries that aren't safe. And what the report revealed was that DIY or conversion kit vehicles are more likely to be involved in fires. So this is where you have a conventional bike and you can buy a conversion kit that involves an electric motor, a battery pack and a controller that you can fit to your existing bike to convert it into an e-bike. And the problem is the quality of the systems being delivered and the way they're applied to the bike has an important role in safety. And what the report also revealed was there's a strong correlation between safety and the price per unit energy. So the lower the price you pay for your batteries or your charger or your system, the lower the manufacturing and quality you tend to get. Sometimes you get safety features that are absent or poor environmental design, allowing water to get into bike battery packs, for example, or missing or unsophisticated battery management units that don't really provide effective protection against stopping the cell from going into thermal runaway. And there's also an issue with user activity. So people being careless and charging batteries with incompatible equipment, perhaps the cell they've been using or the battery they've been using fails, they buy a cheap alternative, but it's not compatible with the original charger. Or the other way around, the charger breaks down, so they buy a cheap generic charger that's claimed as being universal, and they use that to charge their cell, but actually the two aren't compatible, or the protection systems aren't there. And sometimes it can be charging in incorrect or unsafe environments. So, for example, near heating equipment. And again, sometimes people are tampering or bypassing the battery management unit. Now, the issues aren't limited to personal light electric vehicles. There are other sectors that use lithium-ion batteries that are affected by similar issues. And the report touches on work that's underway to try and improve legislation, standards and testing relating to the ability to buy lithium-ion batteries, particularly related to personal light electric vehicles. For example, there's nothing in the standards relating to conversion kits. And when it comes to people buying cells individually, if they want to try and build their own battery packs, there are some inconsistencies there. And user and consumer awareness needs to be improved also. The government has recently launched a Buy Safe, Be Safe campaign to try and deliver 3 key messages, which is really only buy products from reputable sellers, only replace items with things that are recommended by the original manufacturer. And if you are going to try and convert a bike to e-bike, or you need to get your e-bike repaired, seek professional help. Don't try and do it yourself. And if you want to read the report, that's the details there. Just look on the internet and search up the report title. It's quite easy to find. And I think the key thing is that people need to understand that lithium-ion batteries are not like the rechargeable batteries of old, where you could use them, abuse them, and if you weren't careful with them, they just stop working. With lithium-ion batteries, if you try and make them do something that takes them outside that safe operating area, the consequences can be quite catastrophic. Now, what about EVs? Well, here we've got a different situation. So this picture is of an EV with the body removed, essentially. So you have an electric motor at one end, you may have an electric motor at the other end on the other axle, and the batteries tend to be built into the chassis below the floor pan or under the middle of the vehicle. And that's what can sometimes cause problems with firefighting and EV fire, because it's hard to get the water onto the cells that are overheating. And within an EV, you've got very sophisticated monitoring systems. So in order to get the maximum performance out of the battery, they have to monitor the current voltage and temperature of the cells very, very carefully. A lot of work is done to provide the driver with an estimated state of charge. And again, that means having a good understanding of what's going on inside the battery. There's extensive built-in protection systems as well. So within that large battery pack, there will be automatic disconnects that disconnect sections of the battery or cells, individual cells themselves. And there's very careful management of the charging process, as well as active cooling while the vehicle is in use. And the charging is very carefully controlled. There's a process of negotiation between the charger and the EV during charging. So they have a conversation when you connect the EV to a charging station to make sure that both the charger and the EV are happy to begin charging before they do, and the charging is carefully monitored throughout. And there are some calls actually for taking a similar approach to personal light electric vehicles and the charging of batteries there, that there should be more of an automatic process that prevents an incompatible pair of battery and charger from being connected together. But we are seeing electric vehicle fires, obviously, and these are some of the issues that can occur. So I said earlier on that when lithium-ion batteries are made, they're still forming during the first few charges. And new vehicles are often charged just before they are transported. And if there has been a cell defect introduced during manufacture, it might not actually take effect once the cell has been charged a few times. EVs aren't always dead when it comes to being transported, but the ignition's not on. There's still parts of the vehicle that are still alive. And of course, that's true for conventional fueled vehicles also. There are a number of systems that stay live when the vehicle's not in use. And this can be related to things like keyless entry and starting functionality. With EVs, the battery packs are cooled when they're in use, but obviously that can't happen during transit. So if for some reason the EVs get exposed to temperatures that are too high, you could send the cells into thermal runaway. And as you've no doubt heard, they're very difficult to extinguish. New technologies are being developed to try and get rid of that flammable electrolyte, but we still have the problem of toxic gases being emitted from lithium-ion batteries that are also a risk. So how about investigating a lithium-ion battery fire? Well, it's like any fire, really. We have to establish all the relevant background information, not just about the battery, but about all the other possible causes of fire. Find out how the fire was discovered, what appliances or items were seen to be involved early on. If it is a lithium-ion battery, it's important to get a good understanding of the history of the appliance, whether it was being charged and how it was being charged. Is there any replacement equipment being used? And get an idea of the age and condition of the appliance. Has it ever been modified? Has it ever been dropped or damaged? Digital records can sometimes help to pinpoint a fire where the fire's been quite rapidly established and quite severe. Sometimes CCTV can really help understand where a fire started. And a good examination of the scene is crucial in order to scrutinise the patterns of fire damage to determine the most likely seat of the fire and understand what items were in that area. When it comes to lithium-ion batteries, careful identification and inspection of the remains is necessary, together with steps to preserve the relevant evidence for further examination. And it's important, as always, to consider all the plausible sources of ignition. And some of the problems that are raised by lithium-ion battery fires for us as investigators are, well, was it cause or effect? If you have a charged lithium-ion battery that gets heated as a victim of the fire because the fire started somewhere else, it could still go into thermal runaway, and the result afterwards, it will look the same as a cell or a lithium-ion battery that failed and caused the fire. Assumptions, because there are so many fires, videos on the internet these days of lithium-ion batteries failing in a catastrophic way, I think there's, a lot of the time there's an assumption that if there's been a fire or an explosion and there's a lithium-ion battery in the room, that might be the cause. So careful investigation is needed to check that's really the case. It can be difficult sometimes to prove the origin of the cell because there's not much left of markings after the fire. And that's where exemplars can be really helpful in understanding where a battery may have originated and also what faults may be inside the cell when it was produced. The cells can sometimes be projected across a compartment and start fires remote from the original location of the origin of the fire. So you can get misleading patterns of damage where it might look like there's a fire with multiple seats, and actually that's not the case. And sometimes we'll have to excavate quite a large area to find all the component parts of the cell where they had been ejected across an area. And a key consideration for us is safety of the work on site and during exhibit retention. If you have a fire damaged battery that's only partly fire damaged and the undamaged parts of it still retain charge, there's a possibility that it could go into thermal runaway sometime after the fire, either while we're investigating on site or while we are transporting the cell for storage and examination, or during the examination itself. So just an example here, this was a small fire in an office I did a number of years ago. There was a cabinet where the worst burning damage is shown, which had some laptops in it. And in this particular case, the damage was restricted, but on the opposite side of the office where there was no fire damage, stuck to the floor, I found the remains of an ejected cell. Didn't cause a problem here, but if that had landed in something like a waste paper basket or something else that could burn, it could have started a second area of fire damage, and that could have led to misinterpretation of the fire as having multiple seats and therefore possibly having started deliberately. So in summary, lithium-ion batteries are ubiquitous and they are now involved in all aspects of our lives. And it's all because of this high energy density. Our demands are increasing and the technology is evolving. So the cells and batteries are getting bigger, both in terms of electrical capacity and physical size. But I want to emphasize that properly designed, made, handled, used and disposed of, lithium-ion batteries can be safe. Just think about the many millions that are in use daily with no issues. The problems tend to occur when there are design and build compromises, where cost versus quality suffers, or perhaps insufficient protection is built into the systems involved in using the batteries, or when there's poor handling during shipping or during use, or improper charging practice and poor use by the user. And of course, improper disposal. We're seeing a number of fires in waste recycling centres where people are just discarding lithium-ion batteries into the waste stream, and they're causing problems there. So lithium-ion batteries, they're not as benign as the older chemistry batteries we used to for our rechargeable batteries. Again, it's this energy density thing. The thing that makes them useful also makes them problematic. But the cell design is evolving. New chemistries are being researched to look at ways of getting rid of that flammable electrolyte. They tend to be better in some ways, but there's usually a trade-off in some other way, in that you often end up getting less performance for an advantage somewhere else. And standards, education, awareness and legislation will have an important role in ensuring safety. And there's some work to do there in ensuring that those are improved. So we'll move on to taking any questions. Just while the ones that came in on the chat are being collated, I just want to introduce the next in the series of webinars, which will be presented by my colleague Ian Tatner on the illicit cultivation and processing in cannabis and the ways it can cause fires. So we'll move on to taking some questions. And there were some that were submitted in advance. There were quite a few submitted in advance, and I apologise we're not going to get a chance to go through all of them. One of them was how important is managing the charging time? And hopefully you've seen from the presentation that safe operating window, correct charging is critical, both in terms of how long the battery's on charge for and how much current is used in charging to prevent it from being overcharged, because that can lead to thermal runaway. Another question was, given the increasing incidence of lithium fires, what's happening in terms of greater regulation on standards for lithium products? And again, hopefully I've touched on it in the presentation, that it's been recognised that there is a gap, and it's allowing unsafe batteries to go into the public hands, or the public are not using them correctly, and measures are being taken to try and start improving those. So I'll stop sharing now, and hopefully some questions are available for me to look at.
Thank you, Richard. So we've got a few that have come through in the chat. If we could just go through some now. So the first one is, can you please explain the differences with lithium-ion cells and lithium-ion phosphate cells? Manufacturers of the latter suggest they are safer. Is this true?
So this is what I was talking about, the difference between sort of the NMC cells, the conventional earlier chemistry, and the LFP batteries, where what they're saying is because of the change in chemistry inside, when or if you get a failure, you don't tend to get the oxygen produced, so they don't tend to burn. However, they do tend to produce hydrogen instead. So in the right circumstances, there is a risk of an explosion instead. So safer in some ways, but they offer, as with all lithium-ion batteries, better safety in one way seems to sacrifice something else.
Thank you. Another one we have is, when withdrawal notices are issued, are these extended to manufacturers in China? For example, are we restricted to certain countries?
Oh, that's a difficult one to answer, because I'm not really involved in sort of the withdrawal notice process. But what I've noticed is, it used to be the case that if you had a product that was manufactured overseas, then it was very difficult to get any kind of traction from the end manufacturer. And I think that's beginning to change. So I'm not quite sure that answers your question, but so it's not something I'm too heavily involved in myself.
Thanks, Richard. So we have another one, which is, do EVs store data on charging or use?
So again, EVs are not something I'm too heavily involved in, but I expect they would. The problem with stored data on EVs is getting hold of it. So I can see there would be a real advantage for the manufacturers in tracking performance of the cells, of their products, and how the batteries are used, and using that to feed forward into future manufacturing. But if they do record that sort of data, it tends to be considered to be their property. So getting hold of it can be a problem.
Thank you. The next one is, I've heard of solid state battery being developed. Is there much known on this, security and performance wise?
So yes, solid state batteries are being looked at, as other sort of metal oxides being used. So sodium batteries are being researched at the moment, and the reason for the solid state electrolyte is to try and get rid of the electrolyte, the flammable electrolyte in the battery. Other areas of research are looking at non-organic sort of aqueous electrolytes. There can be a problem there because lithium in its metal form really likes to react with water quite vigorously. So there's some work there. They're active areas of research. I'm not quite sure they're going to be with us anytime soon. They would be better from a safety point of view. I'm not quite sure what was meant by security.
Thank you, Richard. So we've got another one, which is, we are seeing considerable costs in the cleanup of battery fires. How dangerous are the traces left after a runway event?
I think this is something we need to try and understand a little bit more about, because I've seen some claims where we've been involved, and because a lithium-ion battery fire has been involved, it's been recommended that some quite extensive cleaning procedures were taken. Again, the post-fire cleanup is not something I'm involved in, but I can see from the chemistry and the things that get emitted from the batteries when they fail, that they do produce different chemicals. That said, taking an average house fire, I can imagine that you get quite a nasty concoction of gases and soot products anyway, just from the things that tend to burn.
Thank you, Richard. There's still a few more questions coming through. Um, We've got one here. So is it true that LFP is gradually replacing lithium ion, or are they both required for different applications? Again, it's kind of in relation to an electric vehicle, so I don't know how.
Yeah. So my understanding is that LFP is sort of the chemistry of choice in lithium-ion batteries for EVs. I mean, they're both forms of lithium-ion battery chemistry, so they're not replacing lithium-ion batteries. It's just a different form of lithium-ion battery chemistry. But yeah, my understanding is that the LFPs are used a lot in EVs.
Thank you. Someone's asked, given the comment on rupturing cause and effect together with so many potential external causes, what are the prospects for recovery in battery fires?
It's not as bad as you think, actually, and that all depends on whether we've got any exemplars available. So we've had cases in the past where you've got a seat of fire. There are a number of potential causes. The usual fire investigation process allows us to rule out a lot and get down to one or two things. And although there may not be much of the actual original lithium-ion battery or cell left, the owner may well have a second battery that they bought that was elsewhere at the time of the fire. An examination of that reveals that there are actually defects within it. And so the two together lead you to sort of form the view that on balance, it was the lithium-ion battery. So each case has to be treated individually, ultimately.
Thanks, Richard. We are overrunning now, so I think we're going to try
Okay.
and wrap it up now. But
Okay.
thank you, everyone, for all of your comments, for getting involved. And again, the webinar will be available on our website later on. And please do come and join us for the rest of the fire series.
Okay. Thank you very much for attending.